500 million years ago, long before forests, long before animals walked on land, the world belonged to the sea. The oceans covered almost everything, and every living thing, every cell, every drifting creature belonged to the sea. Water was not just a home, it was protection. It softened the heat of the sun. It shielded fragile bodies from drying out, and it kept the chemistry of life in balance. The land was empty. No movement, no sound, no life. For billions of years, stepping onto it meant death. And then something began to change those waters. Somewhere in Earth's deep past, life began to appear at the edge of the ocean, as if something unseen was pushing it there. But what forces pushed living things to abandon the only world they had ever known? And why was this desperate escape the beginning of everything that followed? Tonight, we drift into the evidence written in stone, chemistry, and the quiet gaps left behind by vanished seas. But before we begin, if you enjoy these slow journeys into deep time, I'd love it if you gave this one a like and perhaps tapped subscribe. And if you'd be so kind, let me know in the comments, where are you listening from tonight and what time is it there? It's always a joy to see just how far across the world these sleepy science stories travel. So now take a deep breath, let your shoulders relax, and together let's step softly into the moment when the ocean could no longer protect life. For most of Earth's deep history, the planet above the waves was not a place of promise or possibility. It was a surface of silence and exposure, bare rock under an unforgiving sky. No soil softened the land, no shade broke the light, no living skin covered the stone. The continents existed, but they were empty, scorched by sunlight, scraped by wind, and stripped of moisture almost as soon as it touched them. Life did not look toward those shores, because nothing there could hold it. All living things were bound to water, not by choice, but by necessity. The ocean was not simply a habitat, it was a shelter, a cradle, and a barrier against forces that early life could not withstand. Beneath the surface, liquid wrapped every cell in a steady embrace, cushioning it from violent temperature swings and guarding fragile chemistry against disruption. Heat rose and fell slowly, giving molecules time to adjust. Cold crept in gently, never suddenly enough to tear structures apart. In water, change happened at a pace life could follow. The sea also acted as a filter between life and the sky. Long before protective gases softened sunlight, radiation poured down onto the planet unchecked. On land, that energy shattered bonds and unraveled the delicate machinery of early cells. In the ocean, depth became armor. Even shallow water scattered light, thinning its force layer by layer. A few meters could mean the difference between stability and destruction. The surface shimmered with danger, but below it, the world grew quiet and survivable. Water solved another problem that land made unavoidable. It prevented drying. Early life was built on chemistry that only functioned when fully immersed. Membranes collapsed when moisture vanished. Reactions stalled. Structures meant to flex turned brittle and failed. On the continents, evaporation was relentless. Any exposed cell lost its internal balance in moments. In the sea, the surrounding fluid replaced what was lost, keeping internal conditions steady and reactions alive. Gravity, too, behaved differently beneath the waves. Buoyancy softened its pull, allowing simple forms to spread and grow without needing rigid support. Cells could drift, cluster, and experiment with new shapes. Energy that might have gone toward resisting collapse could instead be invested in complexity. The ocean did not demand strength or structure, it offered forgiveness. Over immense spans of time, life adjusted itself perfectly to this aquatic existence. Chemistry, Form and function aligned with water so completely that no alternative seemed possible. There was no reason to imagine survival elsewhere. The land offered no food, no refuge, and no continuity. It was an interruption, not an extension of the living world. From within the oceans, Earth may have seemed complete. Currents carried nutrients, light fed shallow ecosystems, darkness held quieter processes below. Everything life required arrived suspended in solution. To leave this environment would mean abandoning every protection at once, trading stability for exposure and predictability for risk. In this early world, survival depended on staying submerged. Every advantage pointed downward, not outward. Water was not just where life began, it was where life belonged, where every rule made sense, and where existence remained possible at all. The idea of stepping beyond that boundary had no meaning yet, because nothing living had the tools to endure even a moment outside the sea. The oceans did not fail all at once. Their shift began quietly, written first in chemistry rather than catastrophe. For vast stretches of time, the seas had moved with a steady rhythm, cycling nutrients, gases, and minerals in balances that sustained everything living within them. Then, in certain intervals of deep time, that rhythm faltered. Layers of rock formed during these periods carry subtle but unmistakable signals that something fundamental had changed beneath the surface. Sediments that once recorded thriving marine communities suddenly thin or alter in texture, as if life itself had retreated. Fossil rich layers fade into stretches of stone, where shells, skeletons, and microbial traces grow sparse. Entire groups that had persisted for millions of years simply vanish from the record. This absence is not localized or gentle. It appears across distant basins and ancient shorelines, linking seas that were never connected by geography, only by the chemistry of a shared planet. These losses unfolded with startling speed when measured against the slow pace of geological time. Marine diversity dropped sharply, not gradually. Ecosystems that had been layered and complex flattened into simpler forms. Food webs shortened. Species that depended on stable conditions found none remaining. The ocean, once a buffer against sudden change, became a source of stress itself. The cause was not a single blow, but a cascade. Shifts in volcanic activity altered the chemistry of seawater, loading it with elements that changed how oxygen behaved. In some regions, oxygen became scarce, sinking out of reach of animals that relied on it. In others, chemical reactions locked vital nutrients away or released compounds that disrupted cellular processes. The water still moved and flowed, but it no longer supported life in the same way. What makes these events remarkable is their global reach. Separate oceans responded together as if tied by invisible threads. This tells a story not of isolated collapse, but of planetary systems pushed beyond a threshold. Atmospheric changes influenced ocean circulation. Continental weathering fed new materials into the sea. Temperature shifts altered currents that once distributed oxygen evenly. The ocean failed because the planet itself was changing, and the water could not remain untouched by those transformations. For life adapted to stability, this was devastating. Many organisms were built for narrow chemical windows, their bodies tuned to precise balances of oxygen, acidity, and temperature. When those balances drifted, adaptation could not keep pace. Extinction followed not from violence, but from incompatibility. The sea no longer matched the needs of the creatures it had once sheltered, yet the oceans did not become empty. Even at their most hostile, pockets of resilience remained. Microbial communities persisted where conditions allowed, reshaping ecosystems around survival rather than abundance. These survivors altered the chemistry further, sometimes stabilizing their surroundings, sometimes intensifying change. Life continued, but it did so unevenly, fractured across depths and latitudes. In the rock record, these moments stand out as breaks in continuity. They mark the first times the ocean proved unreliable, capable of turning against the life it carried. From these intervals forward, the idea of the sea as an eternal refuge no longer held true. Stability could end, safety could dissolve. The world beneath the waves had shown, for the first time, that it too could fail, reshaping the course of life long before any creature imagined another place to exist. Water once carried breath invisibly, dissolved and drifting through every current. For ages, that quiet abundance had been enough. Then, in certain stretches of deep time, oxygen began to retreat from parts of the sea, not in a sudden withdrawal, but in a slow thinning that spread across basins and depths. The surface might still have shimmered with light, yet below, the water grew heavier and less forgiving, altering how life moved and survived within it. The loss followed patterns shaped by circulation and temperature. Warm waters held less oxygen, and as the planet's climate shifted, layers of the ocean stopped mixing as freely. Dense, depleted water settled into the depths, while fresher layers skimmed above, sealing the boundary between them. What had once been a single breathing body became divided, its lower reaches starved of renewal. In these stagnant zones, oxygen was used faster than it could be replaced. Animals responded not with panic, but with quiet failure. Gills that once drew life from passing currents found little left to capture. Muscles weakened as metabolism slowed. Movement became costly, then impossible. Creatures adapted to steady conditions could not simply wait out the change, because the water itself no longer met their basic needs. Suffocation did not arrive as a dramatic event, but as an exhaustion that spread through entire communities. As oxygen vanished, chemistry shifted again. Elements that remained harmless in well aerated water began to behave differently in its absence. Iron and sulfur reacted, forming compounds that further limited habitability. Microbes flourished in these altered conditions, consuming what oxygen lingered and reinforcing the cycle. The seafloor darkened with layers that spoke of stillness rather than flow, of environments where decay outpaced renewal. The rock record preserves these moments with a quiet precision. Certain sediments contain minerals that only form when oxygen is scarce, their crystal structures locking in evidence of suffocating waters. Fossils disappear abruptly from these layers, not scattered or broken, but simply gone, as if life had withdrawn from that space entirely. In some regions, laminated rocks form, their fine lines undisturbed by burrowing or grazing, signs that few animals remain to stir the mud. These conditions did not remain confined to isolated depths. Over time, oxygen poor zones expanded upward and outward, squeezing habitable space into thinner bands near the surface. Coastal shelves, once rich with life, became unpredictable places where oxygen levels rose and fell with changing currents. Survival demanded flexibility, tolerance, and movement qualities not all organisms possessed. Despite the danger, the ocean did not become lifeless. Patches of stability persisted, where circulation restored balance, creating refuges amid decline. Life clustered there, dense and competitive, while vast areas beyond grew quiet. The sea still held water, still moved with tides and storms, but its ability to support complex life had narrowed. Through these episodes, the meaning of breath changed. Oxygen was no longer a given, but a constraint that shaped where life could exist and how it functioned. The oceans, once generous and evenly supportive, revealed limits that had not mattered before. In learning to endure these breathless waters, life was forced into new arrangements, reshaping itself within a sea that could no longer fully breathe. As oxygen thinned and circulation weakened, the chemistry of the oceans continued to drift into unfamiliar territory. Water that had once diluted and dispersed harmful substances now held them close. Metals released from the planet's crust accumulated slowly, carried by rivers and volcanic pulses into seas that could no longer flush themselves clean. Iron, copper, and other elements lingered longer than before, settling into basins where life already struggled to breathe. Alongside these metals, sulfur compounds became more prominent. In oxygen poor waters, certain microbes flourished by using sulfur instead of oxygen to fuel their metabolism. Their activity released hydrogen sulfide, a substance invisible in the water but lethal to most complex life. What had once been a minor background process began to shape entire regions of the sea. The water remained clear to the eye, yet it carried a chemical edge that few organisms could tolerate. These changes did not announce themselves loudly. Toxicity built gradually, layer by layer, until thresholds were crossed. Shell-forming creatures absorbed metals into their tissues, weakening their structures from within. Soft-bodied animals experienced disruptions at the cellular level, their internal chemistry thrown off by elements that interfered with essential reactions. Even microorganisms felt the shift, as familiar nutrients were displaced by compounds that hindered growth rather than supporting it. Food chains began to unravel from their foundations. Primary producers that formed the base of marine ecosystems declined or vanished in poisoned zones. With fewer microscopic plants and bacteria able to thrive, energy stopped flowing upward. Grazers starved slowly, followed by predators that depended on them. The collapse did not resemble a sudden crash, but a thinning, as each level lost support and faded from the system. In some areas, the seafloor transformed into hostile ground. Sediments darkened with sulfur-rich minerals, recording long periods when decay outweighed life. Burrowing animals disappeared, leaving layers undisturbed and smooth, a sign that little remained to disturb the mud. These conditions could persist for thousands of years, locking entire regions into states where recovery was slow or impossible. The rock record preserves these poisoned intervals with striking clarity. Certain mineral signatures only form when metals and sulfur dominate the water, and they appear alongside sharp reductions in fossil diversity. Entire assemblages end abruptly, not replaced by new forms, but by absence. This pattern repeats across different oceans and times, suggesting that toxicity was not a local anomaly, but part of a broader planetary imbalance. Life responded unevenly. Some microbes adapted, using the very chemicals that killed others as sources of energy. Their success reinforced the toxic state, further excluding complex organisms. Meanwhile, animals capable of tolerating brief exposure retreated into shrinking refuges where conditions remained marginally stable. Competition intensified in these pockets, while vast stretches of the sea fell quiet. The poisoned seas did more than kill individuals. They dismantled relationships that had taken immense time to form. Predation, symbiosis, and recycling of nutrients all depended on chemical stability. When that stability failed, the intricate web of interactions loosened and broke apart. The ocean still moved, still reflected light, still followed the pull of the moon, but within it, the pathways that sustained life were being erased. Through these toxic phases, the sea revealed another limit. Breath had already grown scarce, and now chemistry itself turned hostile. For life, shaped entirely by water, the realization came slowly, written in extinction and silence, that the environment it depended on could become not just difficult, but fundamentally incompatible with survival. The poisoned waters and thinning breath did not pass without consequence. Over time, these stresses gathered into moments when loss spread faster than recovery, marking the first great marine die-offs in Earth's history. They unfolded slowly enough to seem gentle in the moment, yet in the long view, they stand as sharp boundaries etched into stone. Before them, the seas were crowded with forms that had endured for ages. After them, much of that abundance was gone. These extinctions did not erase life evenly. They selected. Creatures with narrow tolerances vanished first, their bodies too specialized for a sea that no longer held stable chemistry. Entire families of organisms disappeared, leaving no descendants and no second attempts. Shells that once filled sediments by the billions stop appearing altogether, as if the ocean had quietly closed the door on their designs. Some body plans that had evolved over immense spans of time ended completely, their experiments finished. The losses reached from the surface to the depths. Shallow ecosystems collapsed when oxygen fluctuations and toxins swept across continental shelves. Deeper communities suffered as stagnant waters expanded, cutting off what little renewal they once received. Reef-like structures built by early organisms broke down as their builders failed, releasing stored carbon and nutrients back into the water in destructive pulses. With each collapse, the sea grew less complex, simpler in structure, thinner in variety. What makes these events remarkable is how close they came to unraveling everything. Life did not retreat to abundance elsewhere. Refuges were small, scattered, and unstable. Surviving populations dwindled to shadows of their former selves, clustered in narrow zones where conditions remained just tolerable. Genetic diversity shrank. Evolution slowed, not from lack of time, but from lack of raw material. The future of life narrowed to what could endure the least hostile corners of the planet. Yet even in this diminished state, life persisted. Microbial worlds proved stubborn, maintaining basic cycles of carbon, sulfur, and nitrogen. They became the backbone of a weakened biosphere, keeping essential processes alive while larger forms struggled or vanished. The ocean continued to function, but at a reduced capacity, its vastness masking a fragile interior. The rock record captures this proximity to collapse with unusual clarity. Long gaps appear where fossils should be. Chemical signatures swing wildly, reflecting ecosystems that could no longer regulate themselves. Layers once rich, with varied remains, flatten into monotonous stone, signaling not transition but interruption. Recovery, when it came, was slow and uneven, measured not in thousands of years, but in spans so long they blur into deep time itself. These first mass extinctions reshaped the living world permanently. What disappeared did not return in the same form. Later life would build on what survived, not on what was lost. The ocean that emerged afterward carried memory in its chemistry, altered by the absence of once dominant organisms. Evolution resumed, but it did so along narrower paths, guided by the constraints carved out by loss. In these early die-offs, Earth revealed a fundamental truth. Life was resilient, but not invulnerable. The margin between persistence and collapse was thinner than it appeared, dependent on balances that could shift beyond reach. The sea still held living matter, still shimmered and moved, but the richness it once supported had been cut back to its foundations. From that reduced world, everything that followed would have to begin again. As the deep seas grew unstable, the shallows might have seemed like places of refuge. Light still reached them, water still moved with tides. Nutrients gathered there, concentrated by waves and runoff from the land. For a time, coastal zones remained among the most productive environments on the planet. Yet it was here, close to the surface and the shore, that danger sharpened most quickly. Shallow water was exposed in ways the open ocean was not. Sunlight heated it rapidly, driving temperatures upward during long days and allowing them to fall just as fast when light faded. These swings placed quiet strain on organisms whose bodies were tuned to steadiness. Metabolism accelerated in the heat, demanding more oxygen precisely when warm water held less of it. Breath became harder to draw at the moments when it was needed most. Pools left behind by retreating tides introduced another hazard. In these isolated pockets, water lingered without circulation. Oxygen was consumed faster than it could be replaced, while waste products accumulated. As hours passed, conditions shifted from merely stressful to lethal. What had been part of a living shoreline became, briefly and repeatedly, a chemical trap. Creatures unable to escape or endure these intervals simply ceased to function. Drying followed heat closely. Thin films of water vanished under sun and wind, leaving tissues exposed to air that stripped away moisture with relentless efficiency. Membranes cracked, cells lost balance. Even brief exposure could undo structures that had never been built to resist evaporation. For organisms whose entire history had unfolded immersed, this was not an inconvenience but an existential threat. Low oxygen compounded every problem. In the shallows, mixing was irregular and unreliable. Calm periods allowed stratification to form, sealing off deeper layers from the surface. When microbial blooms surged, fueled by abundant nutrients, they consumed what little oxygen remained. The water itself became a competitor, demanding breath before animals could access it. Survival depended on either enduring deprivation or escaping it. These pressures did not arrive simultaneously, but their overlap made shallow environments increasingly unforgiving. Heat stressed bodies. Low oxygen slowed recovery. Drying eliminated margin for error. Together, they transformed coastlines into places where life balanced continuously on the edge of failure. Yet these zones could not be abandoned entirely. They were too rich, too central to the remaining food web, and too connected to what stability remained. Some life responded through movement. Mobility offered escape from shrinking pools and suffocating layers. Creatures that could wriggle, push, or drag themselves short distances gained access to better conditions, even if only temporarily. Others altered their physiology, slowing metabolism, tolerating oxygen scarcity, or sealing their tissues against moisture loss. These changes were small, incremental, and often costly, but they offered time. For many, adaptation was not possible. Lineages that had thrived in stable coastal waters vanished as those waters became unpredictable. The fossil record shows their absence not as gradual decline, but as sudden gaps where familiar forms no longer appear. Shallow ecosystems thinned, losing specialists and retaining only those flexible enough to cope with constant fluctuation. Through this slow transformation, the shoreline revealed its dual nature. It was both a bridge and a barrier, offering resources while demanding resilience. Life clustered there not because it was safe, but because it remained usable longer than other options. In adapting to these stressed environments, some organisms began to tolerate brief exposure, to resist drying, to function with less oxygen. The shallows had become a trap, yet within that trap, new capacities quietly formed. What began as survival under pressure laid foundations for possibilities that had never existed before. The boundary between water and land, once meaningless to life, grew increasingly familiar, shaped by heat, scarcity, and the simple necessity of enduring one more tidal cycle. As the seas grew less reliable, another medium quietly waited beyond the surface. Air had always been present, drifting above the waves, largely irrelevant to life shaped entirely by water. Yet, its physical nature held an unexpected advantage. Oxygen behaved differently there, spread freely rather than dissolved, abundant rather than scarce. What had become a limiting resource in the ocean existed in far greater concentration above it. Water binds oxygen loosely, and only so much can be held at a time. Temperature, pressure, and circulation all govern how much breath the sea can store. As those factors shifted, oxygen slipped away from living tissues with little warning. Air, by contrast, was not constrained in the same way. It carried oxygen as a primary component, not as a dissolved trace. Even as planetary conditions fluctuated, the atmosphere remained comparatively rich in this essential element. For organisms accustomed to extracting oxygen molecule by molecule from water, this difference was profound. Breathing in the sea required constant flow. Water had to pass across delicate surfaces, delivering its limited supply while carrying waste away. When oxygen levels dropped, no amount of effort could compensate. In air, oxygen surrounded the body uniformly. It pressed gently against exposed surfaces, ready to diffuse inward without the same resistance. The mechanics were simpler. Gas moved faster than liquid. Exchange happened more quickly. A single breath of air offered more usable oxygen than an equivalent volume of water. For tissues under stress, this meant relief. Metabolic processes that had slowed or failed in suffocating seas could resume with less effort. Energy once spent forcing water across membranes could be redirected toward growth, repair, and motion. This advantage did not make air welcoming. It remained dry, harsh, and unfiltered, stripping moisture from unprotected tissues and exposing cells to radiation and temperature extremes. Yet in one critical aspect, it offered consistency where the ocean no longer could. Oxygen above the surface did not vanish in stagnant layers or get locked away by chemistry. It was there continuously, waiting to be accessed by any structure capable of using it. For life pressed to the edge by low oxygen waters, this difference mattered deeply. Even brief exposure to air could provide a surge of energy, a momentary escape from the constraints imposed by depleted seas. Organisms lingering near the surface, in tidal zones or floodplains, encountered this contrast repeatedly. Each contact reinforced the same pattern. Air was dangerous, but it was generous with breath. Over time, structures that could tolerate gas exchange without collapse gained subtle advantages. Surfaces became sturdier, internal channels retained moisture. Simple air-filled spaces allowed oxygen to reach deeper tissues. These changes did not transform life overnight, but they shifted the balance. Survival favored those that could exploit even small windows of access to the atmosphere. In a world where water no longer guaranteed oxygen, this strange abundance became a resource too valuable to ignore. It altered the equation of survival. Endurance in suffocating seas required constant compromise. Contact with air, however brief, offered stability in a single essential function. Breath became easier to obtain, even if everything else remained difficult. This advantage reshaped how life interacted with its environment. The boundary between sea and sky, once meaningless, gained importance. Above the waves lay a reserve of energy that did not depend on currents or chemistry. Below them, oxygen had become uncertain. For organisms navigating collapsing ecosystems, this contrast influenced where they lingered, how they moved, and which adaptations proved worthwhile. Air did not invite life upward with comfort or safety. It offered no shelter, no moisture, no protection. What it provided was simpler and more decisive. It held breath freely. In a time when water could no longer do so, that difference mattered enough to change the direction of survival itself. As pressures mounted along the boundary between sea and air, a quiet distinction began to matter. Among the many forms struggling in unstable waters, a few carried traits that allowed them to borrow breath from two worlds. They were still fish in shape and habit, moving through water with fins and scales, yet inside them, structures existed that could draw oxygen from air when water failed to provide enough. These organs took many forms, none of them designed with land in mind. Some were modified swim bladders, thin-walled and richly supplied with blood, able to absorb oxygen when filled with gas rather than liquid. Others relied on vascularized regions of the mouth, throat, or gut, surfaces that could briefly function as breathing interfaces. What unified them was not elegance, but utility. In moments of low oxygen, these tissues kept vital processes alive. The advantage revealed itself gradually. In stagnant pools where dissolved oxygen fell, these fish rose to the surface and gulped air, replenishing what water could no longer supply. In warm shallows, where heat stripped oxygen from solution, they endured longer before exhaustion set in. During toxic blooms or chemical swings, brief access to atmospheric breath meant survival rather than collapse. This ability did not free them from the sea. They remained dependent on water for movement, feeding, and protection. Air was used sparingly, a supplement rather than a replacement. Yet, in a world where many species failed for lack of oxygen, even temporary relief proved decisive. Populations that could endure episodic stress persisted while others disappeared from the record. Their survival reshaped ecosystems in subtle ways. As competitors vanished, these adaptable fish occupied new spaces, feeding where others could not remain. Their continued presence maintained connections within weakened food webs, preventing total collapse in some regions. Predators that depended on them endured as well, sheltered indirectly by this flexibility. The capacity to breathe air rippled outward through the ecosystem, stabilizing more than just a single lineage. The fossil record hints at their importance through continuity rather than abundance. Where many forms end abruptly, these fish persist across layers marked by stress and loss. Their bones and impressions appear before, during, and after intervals when oxygen deprivation reshaped marine life. They did not flourish spectacularly, but they endured, and in endurance, they became bridges between worlds. Using air came with cost. Exposed tissues risked drying. Surfacing increased vulnerability to heat and radiation. Timing mattered, and errors carried consequence. Yet these risks were navigable compared to the certainty of suffocation below. Adaptation favored balance rather than commitment, the ability to move between conditions rather than abandon one entirely. Over long spans of time, these traits accumulated meaning. Each generation refined tolerance, improving control over when and how air was used. Behavioral patterns formed around surface access. Muscles strengthened for short excursions into low oxygen zones. What began as an emergency measure became a stable strategy, integrated into daily survival. In a changing world, these creatures demonstrated a principle that would echo far beyond their moment. Life did not leap from sea to land in a single act. It tested boundaries, explored margins, and relied on intermediates that blurred categories. Breathing two worlds allowed existence within instability, a way to persist when environments no longer honored old rules. They remained aquatic, yet their bodies carried proof that air could sustain life directly. In doing so, they preserved lineages through crisis and quietly extended the range of what survival could look like. Within their gills, organs, and habits lay a future shaped not by dominance, but by flexibility, written softly into the long story of life adapting when its only home began to fail. The transition did not begin with a step, but with proximity. Long before life could leave the water behind, it lingered at its edges, drawn into places where sea and land overlapped rather than opposed one another. Mudflats stretched wide and shallow, spread thin beneath the sun, coated in films of moisture and life. Here, water arrived and withdrew in slow rhythm, never fully gone, never fully present. These were not land environments yet, but they were no longer fully ocean either. Shorelines gathered the remains of collapsing seas. Nutrients washed in from rivers and tides, collecting in sheltered shallows where productivity remained high even as deeper waters grew unstable. Algal mats spread across soft sediment, trapping water beneath their surfaces and creating living carpets that held moisture long after tides fell away. Beneath them, conditions fluctuated, but they did so predictably, offering brief windows of stability between extremes. Tidal pools became another threshold. Carved into rock or sediment, they filled and drained with regular precision. Within them, fish and invertebrates experienced cycles of immersion and exposure, oxygen, abundance followed by scarcity, cooling followed by heat. Survival required endurance rather than comfort. Those unable to tolerate change vanished quickly. Those that remained became accustomed to unpredictability as a constant feature of existence. In these environments, the surface was not an enemy so much as a presence. Sunlight reached organisms directly, warming them, energizing microbial growth, and accelerating biological processes. Water depth varied by centimeters rather than meters, making every change immediate and unavoidable. Life here could not rely on distance or depth to buffer it from the world above. Instead, it learned to persist within narrow margins. Movement began to matter in new ways. The ability to push against soft sediment, to wriggle through shallow water, or to brace briefly against gravity allowed access to oxygen-rich air when needed and return to water when conditions worsened. Fins pressed into mud, bodies shifted weight unevenly. Locomotion remained aquatic, but it was no longer exclusively horizontal. Vertical space, however small, gained significance. These places fostered experimentation without commitment. Exposure was brief, retreat remained possible. Organisms that ventured onto damp surfaces did so for moments, not migrations. They fed on stranded material, escaped low oxygen water, or simply endured as tides changed. Each contact with land left subtle marks, favoring tissues that resisted drying, muscles that tolerated weight, and behaviors that balanced risk with retreat. The fossil record preserves this transition indirectly through traces rather than footprints. Sediments show signs of disturbance where animals moved across soft substrates. Burrows shift shape, oriented toward air rather than depth. Skeletal structures hint at stresses different from constant buoyancy. These are not signs of conquest, but of contact, of life pressing gently against a boundary it had never crossed before. What makes mudflats, shorelines, and tidal pools significant is not that they were safe, but that they were survivable. They offered continuity between environments that would otherwise be incompatible. In the open sea, oxygen failed. On dry land, moisture vanished. Here, neither problem dominated completely. Life existed in negotiation, shaped by compromise rather than mastery. Within these marginal spaces, The idea of land became familiar long before it became inhabitable. Organisms learned its textures, its cycles, its dangers, without leaving water behind entirely. The transition began not with intention, but with persistence, with life remaining where it could still function, even as its old world narrowed around it. At the edge of the sea, where water thinned and air pressed close, the boundary softened, and the long movement toward land quietly found its starting place. At the water's edge, movement no longer meant drifting alone. In shallow places, where bodies brushed against mud and stone, fins encountered resistance for the first time. What had once been surfaces for steering and balance began to meet the weight of the animal itself. Each contact with the bottom altered how force traveled through flesh and bone, introducing stresses that water alone had never demanded. Fins were already complex structures, supported by internal rods and muscles capable of fine control. In deeper water, they shaped turns and controlled lift. In the shallows, they began to do something else. Pressed downward, they steadied bodies against currents and waves. Pressed sideways, they prevented rolling as water thinned. Over time, this repeated contact favored fins that could brace, spread weight, and resist bending under load. The change was subtle and slow. There was no moment when a fin became a limb in function or appearance. Instead, certain fins grew thicker near their bases. Muscles reorganized to provide strength rather than speed alone. Internal supports shifted position, aligning more directly with the body so force could transfer efficiently. These adjustments did not free organisms from water, but they allowed control within it, especially where buoyancy weakened. Gravity, once softened by immersion, became a factor that could no longer be ignored. In shallow pools and on damp surfaces, water no longer carried full body weight. Organs pressed downward. Circulation changed with posture. Simply maintaining position required effort. Those able to push against the substrate reduced strain on internal systems, stabilizing themselves during feeding, breathing, or brief exposure to air. Pushing against gravity also enabled new behaviors. Bodies could lift slightly, clearing mouths or breathing surfaces from water that had grown low in oxygen or high in toxins. Heads could rise while tails remained submerged. This partial elevation improved access to air without full exposure to drying or heat. In environments defined by fluctuation, this control proved valuable. Sediments preserve evidence of these interactions. Tracks and impressions show marks consistent with weight-bearing contact, not dragging alone. Patterns suggest coordinated movements, with paired fins working together rather than independently. These traces do not reflect long journeys over land, but brief moments of support, balance, and controlled motion at the boundary between mediums. As fins took on this added role, selection quietly favored robustness over delicacy. Broad surfaces distributed weight more effectively. Joint-like articulations allowed controlled bending rather than collapse. Over generations, these traits accumulated, not as preparation for land, but as solutions to immediate problems of stability and endurance. The earliest limbs did not announce themselves as tools for walking. They were answers to uneven ground and thinning water. By allowing organisms to hold position, to push gently rather than drift helplessly, they reduced energy loss and physical stress. Survival depended less on constant motion and more on controlled stillness when conditions demanded it. This shift carried consequences beyond movement. Supporting weight reshaped the skeleton, influencing how forces traveled through the body. Muscles adapted to sustain tension rather than quick bursts. Sensory feedback from contact with the ground refined coordination. The body began to register solidity, a quality absent in open water. Through these changes, life gained a new relationship with gravity. What had been an ever present downward pull became something to work with rather than against. The ability to press, brace, and lift did not yet open the land, but it expanded what was possible at its edge. In learning to support themselves, these organisms found stability in a world where water no longer guaranteed it, shaping structures that would quietly define the future of movement far beyond the shore. The record of this transition is not written in clear steps, but in fragments pressed gently into stone. Fossils from this period do not announce a clean departure from water. Instead, they reveal bodies caught between ways of living, shaped by both immersion and exposure. These early walkers appear gradually, their forms layered with contradiction, reflecting a world that demanded flexibility rather than commitment. Their skeletons show fins that had not vanished, but changed emphasis. Broad, flattened elements replaced delicate rays near the base, providing strength where fins met the body. Joints allowed controlled bending rather than the fluid sweep of open water. These appendages could still paddle and steer, yet they also bore weight when pressed against sediment. The outline was neither fish nor land animal, but something in between, adapted to shallows, where either role might be required. Heads grew broader and flatter, eyes positioned higher, suggesting a life spent close to the surface. Necks became more distinct, allowing limited movement independent of the body. This change mattered in shallow environments, where lifting the head above water briefly could ease breathing without abandoning moisture entirely. Mouths remained suited for aquatic feeding, and teeth showed little sign of specialization for land-based diets. The body plan retained many oceanic features. Tails remained powerful and laterally compressed, built for propulsion through water. Skin lacked the protections necessary for long exposure to air, relying instead on constant contact with moisture. Sensory systems still favored vibration and pressure rather than distant sound. These creatures could endure moments of exposure, not extended time away from water. Sediments surrounding these fossils offer context as revealing as the bones themselves. They appear in deposits associated with river deltas, floodplains, and tidal zones. Tracks and resting marks suggest brief forays onto soft ground, followed by return to water. There is no evidence of long travel across dry land, only repeated contact with wet surfaces where buoyancy was reduced but not absent. What distinguishes these species is not where they lived, but how they endured instability. Their anatomy reflects compromise rather than specialization. Limbs capable of support existed alongside gills and tails suited for swimming. Lungs or air-breathing structures supplemented, but did not replace, aquatic respiration. Every feature speaks to a life spent navigating fluctuating conditions rather than mastering a new environment. This half-ocean existence offered resilience. When water quality declined, access to air reduced stress. When heat or drying threatened, retreat restored balance. These organisms did not escape the sea. They survived within its changing margins. Their fossils persist across intervals marked by environmental strain, suggesting that this blended strategy provided continuity when extremes eliminated more narrowly adapted forms. In appearance, these early walkers would have seemed familiar yet strange. Fish-like bodies moved through water with confidence, then pressed against mud with deliberate effort. Their limbs pushed rather than walked, lifting and stabilizing rather than carrying them forward in sustained motion. Progress across land, when it occurred at all, would have been slow and deliberate, measured in body lengths rather than journeys. They were not pioneers in the sense of conquest. They did not abandon one world for another. Instead, they inhabited overlap, existing where definitions blurred. Their fossils capture this ambiguity, preserving a moment when life had not yet chosen a direction, only persistence. Half ocean creatures, shaped by both water and air, they embody a transition defined not by departure, but by endurance at the edge, where old solutions still worked and new ones had just begun to take shape. Exposure to air introduced a challenge unlike any life had faced before. Water had always surrounded living tissue, supporting its structure and maintaining the delicate balance of chemistry inside every cell. In air, that balance began to slip away almost immediately. Moisture escaped from exposed surfaces, pulled outward by dryness and motion. Without constant replacement, soft tissues lost their shape, their function, and eventually their integrity. At the smallest scale, drying disrupted everything. Cell membranes relied on fluid surroundings to remain flexible and sealed. As water evaporated, those membranes stiffened and cracked, allowing vital molecules to leak away. Proteins folded incorrectly. Chemical reactions slowed or stopped altogether. What had worked flawlessly in immersion failed quickly when left unprotected. Death did not arrive through violence, but through quiet unraveling. Larger bodies faced the same problem magnified. Muscles stiffened as moisture vanished. Exchange surfaces collapsed, unable to carry oxygen or remove waste. In sunlight, heat accelerated the process, drawing water out even faster. A brief moment too long above the surface could undo hours of survival. For early life, air was not empty space, but an active force stripping away what made living systems possible. Survival demanded a barrier. Skin, once a permeable boundary suited for water, began to change. Layers thickened. Cells produced lipids and proteins that slowed evaporation. Textures shifted from smooth and delicate to tougher and more resistant. These changes did not block water loss entirely, but they bought time, reducing the speed at which tissues dried and allowing brief exposures to become survivable rather than fatal. This transformation altered more than protection. Modified skin also changed how organisms sensed their surroundings, how they moved, and how they interacted with microbes. A tougher exterior offered resistance against abrasion and chemical stress, but it limited direct exchange with the environment. Respiration, feeding, and sensory input all had to adjust to this new interface, reshaping anatomy from the outside inward. Reproduction faced an even greater challenge. In water, eggs developed bathed in fluid, supported and nourished by their surroundings. On land or in drying environments, unprotected eggs lost moisture rapidly. Their contents shrank, membranes collapsed, and embryos failed to develop. For life to persist beyond individual survival, new solutions were required. Egg coverings thickened and diversified. Protective layers reduced water loss and shielded developing embryos from fluctuations in temperature and chemistry. Some eggs retained moisture internally, sealed against the external environment. Others relied on placement in damp substrates or sheltered sites where drying progressed more slowly. These strategies did not free reproduction from water entirely, but they extended its reach into unstable environments. The shift was gradual and uneven. Many lineages failed, unable to balance protection with the need for gas exchange and nourishment. Those that succeeded did so through compromise, reducing exposure rather than eliminating it. Moist microhabitats remained essential. Life clustered where humidity lingered, where shade softened heat, and where protective coverings could do their work effectively. The battle against drying out reshaped bodies and life cycles alike. It favored patience, shelter, and timing over speed and exposure. Organisms learned to emerge when conditions allowed and retreat when they did not. Survival depended on reading the environment carefully, responding to subtle cues of moisture and warmth. Through these changes, air became less destructive, though never benign. Skin and eggs formed the first true defenses against a world without constant water. They marked a turning point, not of conquest, but of tolerance. Life did not overcome dryness. It learned to endure it briefly, carefully, and imperfectly, extending its presence into environments that had once stripped existence away molecule by molecule. Sunlight had always touched the surface of the planet, but for most of Earth's early history it carried a hidden danger. Without a protective veil in the atmosphere, high-energy radiation streamed downward, largely unhindered. To life accustomed to water's filtering presence, this exposure was quietly destructive. Ultraviolet light penetrated tissues, breaking molecular bonds and scrambling the instructions that guided growth and repair. Damage accumulated invisibly, even in brief encounters. In water, this threat was softened. Depth scattered and absorbed radiation, reducing its intensity with every layer. Even shallow immersion provided protection enough for early life to persist near the surface. Outside that shield, however, sunlight acted differently. Cells exposed directly to air faced radiation with no barrier, and their most essential molecules proved vulnerable. Genetic material fractured, proteins lost their structure, systems built for stability began to fail without obvious warning. The danger did not announce itself with pain or immediate collapse. Instead, it showed in failure to divide correctly, in offspring that did not survive, in gradual loss of function. For organisms at the boundary between water and land, exposure had to be brief and carefully timed. A little too much light could undo hard-won adaptations to drying, breathing, and movement. Sunlight became another limit shaping where life could linger. Yet, the same processes that destabilized the oceans were quietly altering the sky. Over immense spans of time, photosynthetic organisms released oxygen as a byproduct of their energy capture. At first, that oxygen reacted quickly with minerals and dissolved compounds, leaving little trace in the air. Gradually, as those sinks filled, oxygen began to accumulate above the planet's surface. This change was slow, uneven, and barely noticeable on human timescales, but its consequences were profound. High in the atmosphere, oxygen interacted with sunlight, forming a thin layer of ozone. This developing shield absorbed much of the most harmful ultraviolet radiation, reducing the intensity that reached the ground. The change was not immediate protection, but a gradual easing of exposure, generation by generation. As the ozone layer strengthened, the character of sunlight shifted. It still warmed, still illuminated, still drove biological processes, but its capacity to destroy at the molecular level diminished. DNA damage occurred less frequently. Repair systems could keep pace. Survival no longer depended entirely on constant shade or immersion. The balance tilted subtly in favor of persistence. This transformation did not make land safe. Drying, temperature swings, and chemical stress remained formidable challenges. Yet one invisible barrier had begun to form between life and the sky. Exposure that had once been fatal became survivable for longer periods. Organisms lingering at the surface gained time, enough to feed, move, and reproduce without immediate penalty. The fossil record reflects this shift indirectly. As oxygen levels rose, signs of sustained activity near the surface became more common. Evidence of brief land contact grew more frequent and more consistent across regions. Life still favored damp environments, but it no longer withdrew as quickly when sunlight struck uncovered tissue. Sunlight had not changed in nature, only in effect. What had once been a silent killer became a manageable presence, its danger reduced by a transformation unfolding far above the living world. The atmosphere itself became part of life's support system, not through intention, but through accumulation and interaction over time. Through rising oxygen and the slow assembly of protection, the planet reshaped the rules of survival. Life did not shield itself directly from the sun. Instead, it altered the world around it, and in doing so, softened one more barrier between water and land. The path forward remained narrow, but it was no longer scorched, completely bare by light from above. When plants first established themselves on land, the surface of the planet began to change its behavior. What had once been bare, shifting, and easily stripped by wind and water gained a living cover that held it in place. Thin mats of early vegetation spread across damp ground, their roots and filaments binding loose particles together. Soil began to form where none had existed before, shaped slowly by organic matter accumulating and decaying in place. This stabilization altered how land interacted with the elements. Rain no longer rushed across stone unchecked. Water lingered, soaking into newly formed soil instead of washing it away. Temperature swings softened as moisture and plant cover moderated heat and cold near the surface. For the first time, land offered pockets of relative consistency rather than constant exposure. These changes were subtle, but they transformed the margins where life had struggled to persist. Plants also changed the chemistry of the environment through their own survival. By capturing sunlight and using it to build tissues, they released oxygen as an inevitable byproduct. This process occurred quietly, leaf by leaf, across landscapes that were still largely empty. Over long spans of time, the accumulated effect reshaped the atmosphere. Oxygen levels rose gradually, not in dramatic leaps, but steadily enough to matter. Richer air meant easier breathing. Organisms dependent on oxygen found that it diffused more readily through the environment. Exchange surfaces could function more efficiently. The margin for survival widened slightly, allowing bodies to grow larger, metabolism to increase, and activity to last longer without immediate strain. What had once been a limiting factor began to ease. As oxygen accumulated, it reinforced the protective changes already forming in the sky. Increased ozone further reduced the harshness of sunlight, making exposure less destructive. Together, these shifts created an environment that no longer punished every moment spent above water. Land was still difficult, but it was becoming reliable enough to support complex interactions. Plants also reshaped the flow of nutrients. Their roots drew minerals from rock and soil, then returned them to the surface as organic material when tissues died and decomposed. This cycling enriched the ground, creating food sources for microorganisms and small animals. The land began to host its own web of life, rather than serving merely as an extension of the sea's edge. With stabilized soils and moderated conditions, moisture lingered longer after rain and tides. Shaded spaces formed beneath plant cover, protecting sensitive tissues from drying and heat. These microhabitats became stepping stones across the landscape, allowing organisms to move between wet areas without immediate exposure to lethal conditions. Movement on land no longer required continuous contact with water. The presence of plants also influenced erosion and sedimentation in nearby waters. Rivers carried fewer loose particles, and coastlines became more stable. Shallow marine environments benefited as well, recovering some of the balance they had lost. The boundary between land and sea grew less chaotic, more predictable, shaped by living systems rather than raw forces alone. Through all of this, plants did not act with intention. They altered the world simply by surviving and growing, yet their influence extended far beyond their own needs. By stabilizing land and enriching the air, they created conditions that allowed other forms of life to persist and diversify. The planet became quieter, more buffered, less extreme. This transformation marked a turning point. Life above the waves no longer depended entirely on constant retreat. With ground that held together and air that offered breath more freely, the land began to function as a connected environment. What had been an escape from danger became, gradually and unevenly, a place where life could remain. As the land stabilized and the air grew richer, a new kind of world quietly took shape above the waves. It was not a sudden opening, but a gradual unfolding of possibilities. Where bare stone had once offered little more than exposure, living surfaces now gathered energy, held moisture, and supported growth. For the first time, the land began to function as an environment rather than an obstacle. Food appeared in forms unfamiliar to the sea. Early plants converted sunlight directly into tissue, spreading across soil and rock in low, persistent mats. Their bodies became reservoirs of energy, available not only while alive but long after, as decay returned nutrients to the ground. Microorganisms followed, feeding on organic matter and multiplying within damp soils. The land developed a base of production independent of the ocean, sustained by light and air rather than currents. This abundance reshaped opportunity. For animals adapted to feeding in shallow water or along shorelines, the land offered resources that did not drift away or vanish with tides. Organic material accumulated rather than dispersing, creating predictable sources of nourishment. Scavenging became possible in ways it never had been underwater. Energy could be found without constant movement, allowing bodies to grow heavier and more complex without immediate penalty. Space expanded as well. In the ocean, life crowded into layers constrained by depth, oxygen, and chemistry. Above the waves, room existed in every direction. The land was vast, largely unoccupied, and structured by gradients rather than uniform pressure. Elevation, shade, and moisture varied over short distances, creating a mosaic of conditions where different forms could persist side by side. These variations allowed new ecosystems to emerge. Moist lowlands supported dense microbial and plant communities. Slight rises hosted organisms tolerant of greater exposure. Sheltered depressions retained water longer, acting as refuges during dry periods. Rather than one continuous habitat, the land became a patchwork, each piece shaped by local balance rather than global circulation. Movement through this world followed new rules. Paths were shaped by terrain rather than currents. Boundaries mattered more, as transitions between wet and dry could define survival. Organisms learned to navigate gradients of humidity and light, selecting routes that balanced access to food with protection from stress. The landscape itself became an active participant in life, guiding behavior through structure and texture. The absence of many predators also altered survival. The land began relatively empty of large consumers, offering relief from constant threat. This did not mean safety, but it reduced pressure enough for experimentation. Life could linger, explore, and adjust without immediate competition from established hierarchies. New relationships formed gradually, built on opportunity rather than displacement. Over time, interactions layered upon one another. Plants altered soil, soil supported microbes, microbes attracted grazers, grazers shaped vegetation. Each connection strengthened the land's capacity to sustain life independently. The ocean remained vast and vital, but it was no longer the only place where complexity could arise. What emerged above the waves was not a mirror of the sea, but something distinct. Energy flowed differently. Space was used vertically and horizontally without the same constraints. Ecosystems developed resilience through diversity rather than depth. The land became a place where change occurred locally, allowing life to persist even when conditions shifted elsewhere. This new world did not replace the ocean, it extended life's reach. With food that stayed put, space that invited expansion, and ecosystems free to assemble from the ground up, the land offered continuity when the sea had grown unpredictable. Above the waves, life found not conquest, but stability enough to remain, shaping a living surface that would continue to evolve far beyond its quiet beginnings. As the land matured into a functioning environment, movement away from the shoreline did not happen through sudden ambition, it happened through quiet preference. Organisms lingered longer on firmer ground, then returned less often to the water that had once defined them. Each small shift inland reflected conditions that had begun to favor persistence rather than retreat. One of those conditions was absence. In the sea, life existed within dense networks of consumption. Every layer carried predators, shaped by long competition. Vulnerability followed every movement, and survival depended on constant awareness. On land, especially in its early stages, such pressures were lighter. The spaces beyond the shore were comparatively empty, not because they were safe, but because few creatures yet possessed the traits to exploit them. This openness reduced immediate threat, allowing life to occupy space without relentless pursuit. With fewer predators came a different rhythm of existence. Energy could be spent on growth, repair, and exploration rather than constant evasion. Bodies that might have been quickly eliminated in crowded marine systems persisted longer, long enough for subtle advantages to accumulate. Survival was no longer dictated solely by speed or concealment, but by endurance and adaptability within a changing landscape. Oxygen availability reinforced this shift. Away from stagnant waters and fluctuating pools, air offered a consistent supply of breath. Diffusion occurred freely, supporting sustained activity without the same energetic cost required in water. Movement on land demanded effort, but it did not carry the suffocating risk that plagued compromised seas. Tissues functioned more reliably. Recovery after exertion became easier. This stability favored organisms capable of tolerating exposure for longer periods. More oxygen also supported higher energy use. Metabolism could increase without immediate collapse, enabling stronger muscles and more complex behaviors. Activity could persist beyond brief windows tied to tides or currents. Time itself expanded, offering longer feeding periods and more flexible responses to environmental change. The land allowed energy to be spent deliberately rather than urgently. Energy entered the system differently as well. Instead of drifting past or settling unpredictably, food remained where it grew or fell. Plants captured sunlight and held it in place. Detritus accumulated rather than dispersing. Feeding no longer required constant movement through three-dimensional space. It could happen locally, reducing cost while increasing return. This efficiency supported life that could remain in one area long enough to benefit from its surroundings. As organisms moved inland, they encountered gradients rather than thresholds. Moisture thinned gradually. Light shifted with elevation and cover. Oxygen remained abundant even as other conditions changed. This continuity allowed incremental adjustment rather than forced transformation. Each step inland was small enough to remain survivable, shaped by preference rather than necessity alone. The inland environment also rewarded specialization over general endurance. Sheltered microhabitats supported behaviors and body plans ill suited to constant immersion or rapid fluctuation. Roots anchored plants, burrows protected animals. The land began to hold memory, marked by paths, coverings, and structures that persisted beyond individual lives. Stability increased through accumulation. None of this erased the ocean's importance. Water remained essential, both as refuge and resource. Yet the balance shifted. Inland spaces offered fewer threats, richer air, and energy that stayed put. Life followed these gradients naturally, not by abandoning the sea, but by extending itself into places that reduced constant stress. Through this slow migration, direction emerged without intent. Movement inland was not a goal, but a response to conditions that favored staying a little longer each time. With predators fewer, oxygen steadier, and energy more accessible, the land became not merely tolerable, but preferable. Life continued forward not because it sought dominance, but because it followed stability wherever it quietly formed. As life extended inland, the ocean did not vanish as a habitat, but its dominance weakened. What once offered consistency and protection increasingly delivered uncertainty. The same waters that had nurtured life for vast spans of time became prone to shifts that rippled outward with little warning. Compared to the emerging stability above the waves, the sea grew difficult to rely on. Instability lay at the core of this change. Ocean systems depended on circulation patterns that moved heat, oxygen, and nutrients across great distances. When those patterns shifted, entire regions could change character rapidly. Mixing slowed or intensified, layers formed or dissolved. Productive waters could become stagnant, then recover, then falter again. For organisms adapted to narrow conditions, this variability carried constant risk. Chemical balance followed a similar pattern. Small alterations in temperature, circulation, or atmospheric input changed how elements behaved in seawater. Oxygen levels rose and fell unevenly. Acidity drifted. Metals and sulfur compounds accumulated or dispersed depending on conditions far removed from local ecosystems. These swings were not synchronized across the ocean, creating a patchwork of suitability that shifted over time. Life in the sea had little ability to escape these changes. Movement offered limited relief when entire basins were affected simultaneously. Adaptation required enduring stress until conditions returned, assuming they did. For many organisms, tolerance had limits. When chemical thresholds were crossed, survival became unlikely, regardless of behavior or location. Extinction cycles followed from this instability. Losses did not occur once, but repeatedly. Each cycle removed lineages that had once been abundant and well adapted. Recovery brought new forms, yet these too faced the same vulnerabilities. The ocean became a place of renewal and erasure in equal measure, its ecosystems shaped by repetition rather than continuity. These cycles eroded the depth of complexity over time. Food webs shortened when specialists disappeared. Redundancy decreased. Each extinction reduced resilience, making subsequent disturbances more disruptive. While life persisted, it did so within a system increasingly defined by fragility. In contrast, the land began to offer insulation against such global swings. Conditions varied locally rather than planet-wide. A shift in one region did not necessarily propagate across continents. Chemical processes occurred on smaller scales, buffered by soil, vegetation, and atmosphere. Disturbance remained part of the system, but it unfolded unevenly, allowing refuges to persist. Oxygen availability above the waves remained comparatively steady. Even when climate fluctuated, air continued to supply breath consistently. Chemical toxicity did not build as easily in open atmosphere as it did in enclosed basins of water. The land absorbed change differently, spreading its effects rather than concentrating them. Predation and competition also shaped outcomes differently. In the sea, crowded environments amplified the impact of disturbance. Loss at one level cascaded quickly through the system. On land, lower density and greater spatial separation slowed such effects. Collapse remained possible, but it was less likely to be total. Over time, these differences mattered. Life did not abandon the ocean out of preference alone, but because persistence became easier elsewhere. The sea demanded constant adjustment to shifting chemistry and repeating loss. The land, though challenging, rewarded long-term stability once basic needs were met. The ocean could no longer compete as the sole foundation for complexity. Its vastness concealed volatility that repeatedly erased progress. Above the waves, life found environments where change unfolded more gently and survival depended less on endurance through collapse. The sea remained vital, but it was no longer the safest place to build the future. The move onto land did not happen once, nor did it proceed in a straight line. It unfolded through repetition. Across deep time, life pressed against the boundary between water and air again and again, each attempt shaped by the conditions of its moment. Some ventures lasted only briefly, others stretched across generations before retreat or extinction followed. The land was not claimed by a single breakthrough, but tested through many trials. Different lineages arrived at the edge independently, guided by similar pressures but carrying different bodies and strategies. Some were fish lingering longer in shallow floodplains. Others were invertebrates creeping across damp surfaces where water still clung to sediment. Each arrival brought a new experiment in tolerance, balance, and endurance. The similarities between them were not inherited, but converged, shaped by the same demands of drying, gravity, and exposure. Many of these attempts failed quietly. Fossils mark their presence briefly, then fall silent. Tracks appear in one layer, then vanish. Morphologies hint at adaptation, only to disappear without descendants. These were not dramatic extinctions, but gradual losses as conditions shifted or limits were reached. The land remained unforgiving, offering no guarantee that persistence today would mean survival tomorrow. Failures often came from imbalance. Some forms adapted well to breathing air but lost too much efficiency in water. Others resisted drying but could not feed or reproduce effectively outside their original environment. Timing mattered as much as anatomy. A lineage emerging during a period of climatic instability faced greater challenge than one arriving when conditions were calm. Success depended on alignment between biology and environment, a balance rarely sustained. Even successful adaptations did not always endure. A group might establish itself inland, spreading for a time, only to be erased by later shifts in climate, chemistry, or competition. The land itself changed continually, reshaped by plants, erosion, and atmosphere. Traits that worked under one configuration could become liabilities under another. Progress was provisional, never final. This pattern of repeated invasion and retreat reveals something essential about evolution. Advancement is not cumulative in a simple way. It is layered, with gains built atop foundations that may later crumble. Each attempt added to the collective knowledge encoded in life's diversity, even when that knowledge did not survive directly. Possibilities explored once could be explored again, refined by different lineages under new conditions. The fossil record preserves this multiplicity through overlap rather than clarity. Different forms appear to experiment with limbs, lungs, and skin at different times. Their coexistence suggests not a single march forward, but a landscape of variation where multiple solutions were tested simultaneously. Some overlapped briefly, others never met. Together, they form a tapestry of attempts, most incomplete. What stands out is persistence. Despite repeated failure, life returned to the land whenever conditions allowed. The pressures that pushed it outward did not vanish, and neither did the opportunities. Each extinction cleared space. Each retreat left niches unfilled. The land remained open enough to invite return, even when it resisted occupation. Through many tries, life learned indirectly, not through memory or intent, but through survival filtered by loss. The forms that endured longest were not necessarily the strongest or most advanced, but those flexible enough to persist when circumstances shifted. They carried with them the quiet history of earlier failures, not as lessons remembered, but as traits refined. The story of land invasion is therefore not one of inevitability. It is a record of contingency, of countless beginnings that did not lead forward. That life eventually established itself on land says less about destiny and more about patience. Success arrived not because it was guaranteed, but because life kept trying long enough for conditions, bodies, and time itself to briefly align. From the many attempts that reached inland, only a few lineages carried their experiments forward long enough to endure. These survivors did not succeed because they were strongest or most complex, but because their bodies balanced competing demands without breaking. They retained ties to water while reducing dependence on it, allowing flexibility when conditions shifted. In that balance lay their persistence. Early tetrapod relatives, emerging from fish with robust fins and air-breathing capacity, represent one such path. Their bodies tolerated brief exposure, their limbs supported weight, and their lungs supplemented aquatic respiration without fully replacing it. This combination allowed them to occupy wetlands, floodplains, and forest edges where water remained accessible but no longer defined every moment. Over time, descendants refined these traits, gradually reducing reliance on gills and increasing control over movement on land. Arthropods followed another successful route. Insects and their relatives possessed exoskeletons that slowed water loss and supported bodies against gravity. Their small size reduced strain, and their tracheal breathing systems delivered oxygen directly to tissues. Many reproduced rapidly, allowing populations to adapt quickly to local conditions. Where moisture and shelter existed, they flourished, becoming some of the first fully terrestrial animals to spread widely across land. Other groups did not carry forward. Some early walkers retained bodies too dependent on constant moisture, unable to resist drying long enough to feed or reproduce effectively. Their skins failed under prolonged exposure. Their eggs required immersion. Though they lingered in marginal habitats for a time, changing climates eventually narrowed those refuges beyond sustainability. Certain fish with air-breathing organs persisted for millions of years without fully transitioning. Their success lay in endurance rather than expansion. They survived repeated crises by remaining adaptable, but they did not open new worlds beyond the water's edge. When conditions improved in the sea, they returned fully. When land demanded too much, they withdrew. Their lineage continued, but their role remained bounded. Large-bodied animals struggled early on. Gravity imposed costs that muscle and bone had not yet solved efficiently. Energy demands increased faster than food availability could support. Without stable land ecosystems, These forms faced limitations smaller organisms avoided. Many disappeared not suddenly, but through attrition as environments shifted beyond their capacity to respond. Plants, though not animals, shaped which lineages could succeed. Where vegetation stabilized soil and moderated climate, animal life followed. Where plants failed to persist, animal incursions faded. Lineages tied closely to plant cover gained indirect support, benefiting from shelter, food webs, and moderated extremes. Those arriving too early, before these foundations formed, rarely endured. Success also depended on timing. Lineages that emerged during intervals of relative environmental calm gained footholds difficult to establish during periods of upheaval. Even well-adapted bodies could fail if conditions changed faster than reproduction and selection could respond. Survival was not simply about having the right traits, but encountering the right moment. The fossil record reflects this selective persistence. Some forms appear briefly, then vanish entirely, leaving no descendants. Others persist through multiple layers, changing subtly while retaining recognizable structure. These enduring lines carry continuity, bridging aquatic ancestry and terrestrial future without abrupt break. The lineages that won did not conquer land. They remained cautious, flexible, and responsive. They succeeded by tolerating uncertainty rather than eliminating it. Those that disappeared were not weaker in essence, but less aligned with the shifting balance between water, air, and ground. From many possibilities, only a few matched conditions long enough to persist. Through this filtering, the living world narrowed and strengthened. What remained formed the foundation of terrestrial animal life, shaped as much by disappearance as by success. The land was not inherited by the boldest, but by those whose bodies and behaviors could remain intact as the world slowly rearranged itself around them. Even as life established itself on land, it never fully severed its connection to the sea. The environments that shaped the earliest bodies left marks that could not be erased, only adapted. Inside terrestrial creatures, echoes of the ocean remained, carried quietly in organs, fluids, and chemistry that still reflected an aquatic origin. Lungs, those suited for air, bear this history clearly. They did not arise as entirely new structures, but from tissues once used to manage buoyancy and gas exchange in water. Their branching passages resemble internal shorelines, maximizing surface area to allow gases to diffuse efficiently, just as gills once did in flowing currents. Moisture remains essential within them. Without a thin film of water coating every surface, oxygen could not pass into blood at all. Breathing air still depends on maintaining a controlled internal sea. Blood chemistry carries this legacy further. The balance of salts dissolved within it closely mirrors ancient seawater. Sodium, chloride, potassium, calcium, and other ions circulate in precise concentrations, held within narrow limits that reflect conditions once found outside the body rather than within it. Cells continue to function only when surrounded by this familiar solution. Too much deviation and processes falter, not unlike the failures that once accompanied shifts in ocean chemistry. This internal saltwater does more than support basic reactions. It enables nerve impulses, muscle contraction, and the movement of nutrients and waste. Each heartbeat circulates a fluid that would have been recognizable to early aquatic life. The land may be dry, but within complex organisms, chemistry remains comfortably wet, buffered against the variability outside. Salts also shape how water moves through the body. Osmotic balance determines whether cells swell or shrink, a process that once depended entirely on the surrounding ocean. Modern terrestrial animals still regulate water carefully, retaining or releasing it through kidneys, skin, and respiration to maintain an internal environment that never strays far from its original template. Thirst itself reflects this need, a signal not for dryness of surroundings, but for preservation of the internal sea. Even the way oxygen travels reflects this inheritance. In water, gas exchange depended on moving fluids past specialized surfaces. On land, blood took on that role, transporting oxygen from lungs to tissues in a steady flow. Hemoglobin binds and releases oxygen in response to subtle chemical cues, a system sensitive to acidity and temperature, variables once governed by seawater conditions. The same relationships persist, now managed internally rather than imposed by the environment. This continuity extends beyond animals. Plants regulate salts and water within their tissues, maintaining gradients that echo aquatic constraints. Microorganisms in soil rely on thin films of moisture, carrying out reactions in solutions that resemble diluted seawater. Across land ecosystems, life continues to function as though water were still always near, even when surfaces appear dry. The persistence of these traits reveals something fundamental about adaptation. Moving onto land did not require rewriting life from the beginning. It required preserving what worked and protecting it from exposure. Rather than abandoning aquatic chemistry, organisms enclosed it, built barriers around it, and regulated it carefully against an unpredictable world. Through lungs that require moisture, blood that carries salt, and cells that demand precise balance, the ocean remains present within every complex land organism. It is carried quietly, unseen, through tissues and vessels, sustaining processes shaped long before the first step onto shore. The transition to land did not erase life's origin, it folded it inward. In this way, the story of leaving the sea is also the story of keeping it. Beneath skin and bone, in breath and blood, the ancient environment that once defined survival continues to flow. The land became home, but the ocean remained within, a reminder that life did not escape its first world entirely. It carried that world forward, contained and preserved, into every step taken away from the waves. Even with layers of stone, chemistry, and fossils spread across the planet, parts of this story remain unsettled. Scientists agree that the oceans became unreliable long before life committed to land, yet the exact forces that pushed them into crisis are still debated. The evidence is clear enough to outline what happened, but not precise enough to pin every change to a single cause. One line of thought centers on oxygen itself. Rising oxygen in the atmosphere altered ocean chemistry in ways that may have destabilized long-standing balances. As oxygen entered seawater unevenly, it could have triggered chain reactions that removed oxygen from deeper layers rather than enriching them. In this view, the very process that eventually made land survivable first made the seas more dangerous, shifting where life could persist without warning. Another perspective emphasizes volcanism and tectonics. Massive eruptions and the slow rearrangement of continents released enormous quantities of carbon dioxide, metals, and sulfur into the environment. These inputs changed ocean circulation, acidity, and nutrient flow. Chemical signatures in rock support this influence, yet the timing and intensity vary between regions, making it difficult to link every collapse to a single geological episode. Climate change adds another layer of complexity. Variations in global temperature affected how water mixed, how gases dissolved, and how ecosystems functioned. Warmer oceans held less oxygen. Changing rainfall altered nutrient delivery from land. Ice-free and ice-covered intervals both left their mark on marine life. These shifts overlapped with chemical changes, amplifying stress without leaving a simple signature of cause and effect. Food webs themselves may have played a role. As microbial communities evolved and spread, they reshaped oxygen and nutrient cycles. Some blooms consumed oxygen rapidly, creating localized dead zones that expanded under the right conditions. Others altered sulfur and iron chemistry in ways that made recovery harder. Life did not simply respond to crisis, it participated in shaping it. What remains uncertain is how these factors combined in real time. Geological records are uneven, compressed, and incomplete. A layer of rock can represent thousands of years reduced to a thin line. Fossils appear and disappear abruptly, but the processes behind those changes unfolded slowly. Cause and consequence blur together across deep time, making definitive answers elusive. There is also debate over scale. Some scientists argue for a series of global crises synchronized across oceans by atmospheric change. Others see regional collapses that cascaded outward, overlapping until they resembled worldwide events. Both views find support in different data sets, reflecting the complexity of Earth systems rather than disagreement over evidence itself. Even the decision to frame this history as a crisis invites discussion. From one perspective, life endured and diversified, adapting repeatedly without permanent collapse. From another, entire ecosystems vanished, and paths that evolution might have taken were closed forever. Whether this period is seen as catastrophe or transition depends on which measure of loss or persistence is emphasized. What scientists do share is an understanding of uncertainty itself. Gaps in the record are acknowledged, not ignored. Each new fossil bed, isotope analysis, or refined model adjusts the picture slightly, revealing how much remains beyond reach. The story becomes clearer in outline, while finer details remain unresolved. This uncertainty does not weaken the narrative, it enriches it. The movement of life onto land was not driven by a single switch or moment. It arose from overlapping pressures that varied across time and place. The lack of a simple trigger reflects the nature of Earth systems, complex, interdependent, and resistant to reduction. What remains unknown is not a failure of evidence, but a reminder of scale. The processes that reshaped life unfolded over spans far longer than any individual record can capture. Scientists continue to piece together this history patiently, accepting that some details may never resolve fully. In the quiet space between what is known and what is still argued, the story of life leaving the ocean remains open, not incomplete, but deep enough to continue drawing careful inquiry. For most of Earth's history, land was not an invitation but an absence. Even as life tested its margins, the balance could easily have tipped the other way. The conditions that allowed organisms to persist above the waves were narrow, fragile, and dependent on many factors aligning at once. Without those alignments, Earth might have remained a planet where complexity never fully escaped the sea. The earliest stages of land habitation relied on thin margins of moisture, oxygen, and protection. A slight reduction in atmospheric oxygen would have weakened the developing shield against harmful radiation. A modest shift in climate could have dried emerging soils faster than life could tolerate. Without stabilized ground, erosion would have erased early plant communities before they could establish continuity. Each requirement depended on the others. Remove one, and the entire chain unraveled. The ocean itself nearly reclaimed dominance multiple times. Chemical instability returned in cycles, threatening the very organisms experimenting with life on land. Marine extinctions could have removed the ancestral lineages best suited for transition before they diversified enough to persist elsewhere. In such a scenario, recovery might have favored forms optimized solely for aquatic life, closing the brief window that land offered. Plants played a decisive role, yet their success was never assured. Early vegetation struggled against exposure, nutrient scarcity, and mechanical stress. If these pioneers had failed repeatedly without stabilizing soils and moderating local climates, animal life would have lost critical support. Without shade, moisture retention, and a growing oxygen supply, the land would have remained hostile far longer. Timing mattered deeply. The expansion of oxygen into the atmosphere, the formation of protective ozone, and the gradual cooling of surface temperatures overlapped just enough to permit persistence. Had these processes unfolded in a different order or at a different pace, the result could have been delay or denial. The land might have lingered as an edge, visited but never inhabited. Even adaptation itself carried risk. Bodies evolving to tolerate air exposure risked losing efficiency in water. If conditions had shifted before those compromises stabilized, lineages could have been stranded between worlds, unable to thrive in either. The history of repeated failed invasions shows how easily this balance could collapse. Energy availability also constrained possibility. On land, food initially depended on sparse plant growth. Had productivity remained too low for too long, animal incursions would have faded. Larger, more complex bodies require consistent energy. Without sufficient production, complexity would have stalled, favoring small, resilient forms that might never build extensive terrestrial ecosystems. The persistence of water within bodies reveals how incomplete the separation remained. Land life carried its dependency inward, enclosing the sea rather than leaving it behind. This internal reliance underscores how close life remained to its origin. The transition did not represent a clean break, but a careful negotiation that could have failed at many points. What ultimately allowed land life to take hold was not inevitability, but redundancy and patience. Multiple attempts overlapped. Failures did not end the process entirely. Opportunities reemerged as conditions fluctuated. Over immense spans of time, persistence outlasted instability. Earth's path was therefore contingent. A different sequence of eruptions, a prolonged climate swing, or a slower rise in oxygen could have kept life confined to the oceans. Forests, insects, reptiles, mammals, and humans were not guaranteed outcomes. They rested on a series of balances that held just long enough to allow continuity. The planet came remarkably close to remaining an ocean world, rich with life yet bounded by water. That it did not reflects not destiny, but a long series of narrow survivals. Land life exists because instability relented often enough and long enough for fragile experiments to become enduring ecosystems. If the movement onto land had failed, Earth would not be empty. It would be alive in ways both abundant and unfamiliar, shaped by water alone. The oceans would remain the primary stage for complexity, carrying forests of algae, drifting animals, and microbial worlds layered through depth and light. Life would persist, evolve, and diversify, yet it would do so entirely beneath the surface, bounded by chemistry and circulation. Without animals establishing themselves on land, there would be no footsteps pressed into soil, no wings cutting through open air, no forests animated by motion. The continents would appear largely still, their surfaces shaped by plants and microorganisms alone. Vegetation might spread widely, stabilizing soils and enriching air. Yet without grazing or burrowing animals, ecosystems would follow different patterns. Plant life would grow, die, and return to the ground undisturbed, building thick layers of organic material over immense spans of time. The absence of land animals would ripple backward into the sea. Many marine ecosystems today rely on nutrients delivered from rivers shaped by animal activity on land. Without that interaction, ocean chemistry would follow alternate paths. Some species that exist now might never arise. Others, better suited to stable aquatic conditions, could dominate instead. Evolution would continue, but along channels that never require adaptation to gravity, dryness, or air. In such a world, intelligence might still emerge, but it would be constrained by water. Large brains require energy, and while oceans can support complexity, they limit manipulation of the environment. Fire would not exist. Tools requiring dry space and controlled heat would remain impossible. Communication would rely on movement, light, or sound transmitted through water rather than air. Culture, if it arose at all, would look nothing like what is known. There would be no mammals roaming open ground, no reptiles basking under sun, no birds tracing invisible paths across the sky. Without these lineages, there would be no hands capable of shaping objects deliberately, no upright gaze scanning distant horizons, no persistent memory carried through writing, art, or architecture. The planet would have no observers reflecting on its own history. Earth's surface would feel quieter, not in absence of life, but in absence of movement across land. Weather would still carve valleys, rivers would still wind toward the sea, seasons would still pass. Yet without animals, the land would lack the dynamic feedback that accelerates change and diversity. Evolution would move more slowly, guided by fewer interactions. Most notably, there would be no humans. No species would stand apart from its environment to wonder about origins or futures. The story of the planet would continue unobserved, told only through stone, chemistry, and the slow turning of cycles. There would be no science, no history, no memory beyond what the earth itself retained. The difference would not be moral or emotional, it would be structural. A planet without land animals would still be rich, but its richness would be inward, hidden beneath waves or locked into silent growth across continents. Complexity would exist, but it would never escape the mediums that shaped it. That this world did not come to pass rests on fragile success. The movement onto land allowed life to interact with energy, space, and matter in new ways. From that expansion came faster evolution, richer feedback, and eventually awareness itself. Humans are not separate from this process. They are its distant consequence. Had land life failed, Earth would remain a living planet without witnesses. That it does not reflects a narrow passage crossed long ago, when survival aligned just enough for life to step beyond water and remain there. Earth's history reveals a pattern shaped less by dramatic turning points than by quiet thresholds. Again and again, outcomes depended on changes so small they would seem insignificant in isolation. A slight shift in temperature, a modest rise or fall in oxygen, a gradual alteration in chemistry. Each on its own appeared manageable. Together, they decided whether entire worlds of life could persist or fade away. The balance that allowed life to remain on land was never stable in a permanent sense. It hovered within narrow limits, maintained only because opposing forces offset one another just enough. Oxygen rose, but not too quickly. Ultraviolet radiation weakened, but not completely. Moisture reached inland, but did not linger everywhere. Each factor restrained the others, creating conditions that were workable rather than ideal. When balance held, Ecosystems expanded. When it drifted, contraction followed. The difference between these outcomes was often subtle. A small reduction in atmospheric oxygen could increase radiation exposure enough to slow reproduction. A minor increase in temperature could lower oxygen solubility in water, stressing both marine and coastal life simultaneously. None of these changes required catastrophe. They unfolded through accumulation. This fragility is evident in the repeated cycles of expansion and loss that mark deep time. Life did not move forward steadily. It advanced, paused, retreated, and resumed again. Each phase reflected the environment's sensitivity to small adjustments. Stability was not the default condition. It was an emergent state, achieved temporarily when variables aligned. On land, balance depended on feedback. Plants stabilized soil and enriched air. Stabilized soil retained water. Retained water supported further plant growth. These loops reinforced one another, but only while underlying conditions remained favorable. Disrupt the loop at any point, and the system weakened. Without soil, plants struggled. Without plants, animals lost support. The entire structure rested on continuity that could be broken quietly. The ocean displayed the same sensitivity. Small changes in circulation altered oxygen distribution. Minor chemical inputs shifted toxicity. These adjustments cascaded, affecting food webs and reproductive success. Because the sea connected distant regions, local changes spread widely, amplifying their effect. Balance there was harder to isolate and easier to lose. Earth itself provided no guiding hand. There was no mechanism ensuring outcomes beneficial to complexity or longevity. The planet responded only to physics and chemistry. Life adapted within those constraints, persisting when balance allowed and diminishing when it did not. Survival was conditional, not guaranteed. What makes this history striking is how often balance could have failed entirely. Land ecosystems relied on timing that did not need to align. They relied on redundancy that could easily have been absent. They relied on patience that required countless generations to express itself. The persistence of life above water reflects not inevitability, but resilience operating within narrow margins. Even now, this fragility remains. Modern ecosystems function within limits set long ago. Temperature, chemistry, and atmospheric composition still govern what can live where. The same principles that once decided whether life could leave the ocean continue to shape its future on land. Small changes matter because systems are interconnected. Adjust one component, and others respond. Sometimes feedback restores balance. Sometimes it accelerates imbalance. The difference lies not in the size of the initial change, but in how systems absorb it. Earth's story is therefore not one of permanence, but of calibration. Life exists where conditions remain within workable ranges and fades when they do not. That land life persists at all reflects a long history of adjustments that held just long enough to allow continuity. The world did not need to be perfect. It needed only to remain close enough to balance for long enough. From those narrow windows, forests grew, animals spread, and awareness eventually emerged. Everything that followed rests on that delicate equilibrium, shaped by changes so small they might easily have tipped the outcome the other way. Earth is not unique in facing the challenge of habitability. Other rocky planets formed with water, atmosphere, and energy, yet their stories unfolded differently. Mars and Venus illustrate how small differences in timing, distance, and chemistry can determine whether a world sustains life or loses that possibility entirely. Mars began with promise. Evidence carved into its surface shows ancient river valleys, deltas, and lake beds, shaped by flowing water over long spans of time. Its early atmosphere was thicker, able to hold heat and support liquid water on the surface. Yet Mars was smaller, and that size mattered. Its weaker gravity struggled to retain atmosphere once solar winds intensified. Over time, gases escaped into space, thinning the air and cooling the planet. As the atmosphere faded, water followed. Some froze into the ground, some evaporated and drifted away. Without pressure to keep it liquid, Mars dried slowly but decisively. With less water and a weaker magnetic field, radiation reached the surface more easily, breaking down remaining molecules and further stripping the planet of protection. Habitability was not erased suddenly, it narrowed, then vanished. Venus followed an opposite but equally fragile path. Forming closer to the Sun, it received more energy from the start. Early Venus may have held oceans, clouds, and conditions not unlike those on young Earth, but proximity altered feedback loops. As temperatures rose, water vapor increased in the atmosphere. Water vapor trapped heat efficiently, amplifying warming rather than stabilizing it. This process accelerated. Oceans evaporated. Without liquid water to regulate carbon dioxide through rock interactions, greenhouse gases accumulated unchecked. Surface temperatures climbed until lead melts and no known life can persist. Solar radiation then broke water molecules apart, allowing hydrogen to escape into space. The planet lost its water permanently, locking itself into an extreme state. Mars and Venus demonstrate how habitability depends on balance, not abundance alone. Mars had water, but lacked the mass and magnetic shielding to hold atmosphere long term. Venus had energy and likely water, but crossed a thermal threshold that reversed stabilizing feedback. In both cases, the systems tipped and could not recover. Earth avoided these outcomes by coincidence and timing rather than inevitability. It formed at a distance where water could remain liquid. Its size allowed it to hold atmosphere without crushing it under extreme pressure. Its magnetic field deflected solar wind, preserving gases and water. Plate tectonics recycled carbon, preventing runaway accumulation or loss. None of these features was guaranteed. The same processes that challenged early life on Earth operate on planetary scales elsewhere. Oxygen can destabilize chemistry, carbon dioxide can trap heat, water can buffer temperature or amplify warming depending on context. Habitability is not a single condition, but a network of interactions that must remain within workable ranges simultaneously. What stands out is how narrow those ranges appear. A modest shift in distance from a star can change climate entirely. A difference in planetary mass can determine whether atmosphere persists. A change in rotation or magnetic field strength can alter radiation exposure. Each factor nudges the system toward stability or collapse. Mars and Venus did not fail because they lacked complexity. They failed because their balances drifted beyond recovery. Once crossed, certain thresholds do not reverse. Water lost to space does not return. Atmospheres stripped away do not rebuild easily. Heat trapped beyond control reshapes surfaces permanently. These worlds are reminders that life requires not just opportunity, but endurance. Conditions must remain stable long enough for complexity to adapt and persist. Earth's history shows how difficult that is even when life is present to respond. Without that response, planets follow physics alone. Looking outward, Mars and Venus frame Earth's story more clearly. They show that habitability is not common, even among similar worlds. Earth remains livable not because it was designed to be so, but because it stayed close enough to balance for long enough. That same problem faces every planet, and most do not hold that balance for very long. Life's story is often told as a chain of triumphs, but its deeper pattern is quieter. Survival did not emerge from ideal conditions or gentle encouragement. It arose because environments became difficult, unstable, and at times dangerous. Adaptation followed pressure, not comfort. What endured did so because it had to, reshaped by circumstances that offered little room for error. From its earliest forms, life existed close to failure. Chemistry shifted, temperatures wandered, energy fluctuated. Each change narrowed the range in which living processes could continue unchanged. When balance held, life persisted with minimal adjustment. When it slipped, survival demanded response. Those responses were not planned or purposeful, but filtered through loss. Forms that could not adjust faded. Those that could remained. Danger acted as a sculptor. Oxygen, now essential, once threatened cellular machinery. Dryness tore at tissues evolved for immersion. Gravity stressed bodies shaped by buoyancy. Radiation damaged unprotected molecules. None of these forces arrived as invitations. They arrived as constraints that life either navigated or succumbed to. Adaptation was the residue left behind after repeated removal of what could not cope. This process did not favor perfection, it favored adequacy. Traits that worked well enough under pressure were retained even if they introduced inefficiencies elsewhere. Lungs remained moist. Skin stayed permeable within limits. Internal chemistry required careful regulation. These compromises reflect survival under constraint rather than elegant design. They function because they had to, not because they are ideal. The movement onto land illustrates this clearly. Life did not leave the ocean because land was welcoming. It did so because the ocean became unreliable. Conditions worsened unevenly, forcing experiments at the margins. Each step away from water exposed new threats, yet retreat often meant returning to instability. Persistence emerged only through tolerating danger long enough for incremental change to accumulate. Even success remained provisional. Adaptations that worked in one era failed in another. Extinction followed when danger exceeded tolerance. Survival was never permanent. It was renewed generation by generation, contingent on circumstances remaining within bounds. This cycle repeated across deep time, reinforcing that adaptation responds to challenge rather than opportunity alone. Calling life a miracle obscures this reality. Miracles imply exemption from constraint. Life shows none. It operates entirely within physical law, shaped by forces indifferent to persistence. Survival arises not from exception, but from repetition. Enough attempts overlap with survivable conditions, and continuity appears. Remove danger, and selection slows. Increase it beyond limits, and life recedes. This framing reframes resilience. It is not a stored strength waiting to be revealed, but an ongoing process maintained through exposure. Each challenge filters possibilities, narrowing diversity in one sense while deepening specialization in another. What remains carries the imprint of threats encountered long ago, encoded in structure and behavior. Modern life continues this pattern. Environments shift, resources fluctuate, stress tests physiology and behavior continually. Adaptation does not stop. It rarely announces itself. It unfolds quietly, visible only across long spans of time. Stability is experienced locally, but globally it is transient. Understanding life as a survivor aligns it with the planet that hosts it. Earth does not guarantee persistence. It offers conditions that drift, sometimes gradually, sometimes abruptly. Life persists by responding, not by transcending. Its success lies in staying within margins rather than escaping them. In this light, the emergence of complex life on land reflects neither inevitability nor miracle. It reflects durability shaped by danger. Adaptation arose because conditions demanded it, and only those demands kept refining bodies capable of enduring change. Life continues not because the world is kind, but because survival has been practiced long enough to remain possible. When viewed up close, the movement of life from ocean to land can feel dramatic, even abrupt, yet across deep time, it unfolded at a pace almost impossible to sense. Changes that seem decisive in hindsight stretched across millions of years, passing so slowly that no single generation experienced transition as change at all. What appears as a crossing was, in reality, an extended drifting. Early experiments lingered for vast spans without resolution. Organisms hovered at boundaries, neither fully aquatic nor fully terrestrial, repeating similar patterns generation after generation. Small refinements accumulated quietly, bones thickened slightly, skin altered by degrees. Breathing shifted incrementally. Each adjustment was subtle enough to be invisible in the moment, yet together they reshaped entire lineages. This slowness was not inefficiency, it was necessity. Biological systems cannot reorganize wholesale without collapse. They change through inheritance, filtered by survival, limited by what already exists. Every step depended on what came before, and every advance carried the weight of compromise. Time provided the only space large enough for such negotiation. While change was slow, its scale was immense. The transition did not involve a single species or environment, it altered planetary systems. As life spread inland, it reshaped soils, atmospheres, and energy flow. Weathering increased, carbon cycles shifted, oxygen accumulated. Landscapes that once lay barren became structurally complex, layered with roots, decay, and movement. These effects radiated outward. Marine environments changed in response to altered chemistry and nutrient flow from land. Rivers began to carry different materials. Coastal zones transformed. The boundary between sea and land became dynamic rather than static. What began as biological adjustment became planetary feedback. Deep time reveals how these enormous outcomes emerged without urgency. There was no single moment when Earth flipped states. Instead, overlapping processes ran concurrently, some accelerating, others slowing. Plate movements rearranged continents. Climate wandered through warm and cool intervals. Life responded continuously, its changes braided through physical transformation. The immensity of this timescale also reframes success and failure. Lineages that vanished after a few million years were not brief experiments by any meaningful measure. They endured longer than entire eras of human history. Their disappearance feels sudden only because geological layers compress immense durations into thin records. Loss and persistence both operated on scales beyond immediate perception. From this perspective, patience becomes central. Life did not overcome obstacles through force or speed. It persisted through duration. When conditions closed one path, it waited until another opened. When environments destabilized, it contracted, then expanded again when balance returned. Deep time allowed recovery that would be impossible on shorter scales. The enormity of this process also highlights how interconnected outcomes were. The rise of forests altered climate. Climate shaped erosion. Erosion influenced ocean chemistry. Ocean chemistry fed back into atmospheric composition. Each link depended on others unfolding across millions of years. No single thread explains the whole. Standing within the present, it is easy to underestimate this scale. Human lives occupy moments. Recorded history occupies instants. Deep time stretches beyond intuition, flattening events that reshape the planet into patterns barely discernible. Yet it is within that vastness that the story of life on land makes sense. The transition was slow because complexity requires stability long enough to persist. It was enormous because even slight biological shifts can cascade when given sufficient time. Together, slowness and scale reveal evolution not as a march, but as a tide, advancing and retreating across epochs until the shoreline itself is transformed. Through deep time, life did not rush into its future. It unfolded into it, gradually, repeatedly, and on a scale that reshaped the earth itself. Even after life spread across continents, the sea never released its hold entirely. Its influence lingered, shaping bodies, behaviors, and cycles in ways that reach into the present. The movement onto land did not end an era. It layered new possibilities atop an older foundation, leaving a long shadow that still stretches across modern life. Whales embody this inheritance in motion. Their ancestors walked on land, breathing air and bearing weight against gravity, yet the ocean drew them back. Water offered buoyancy, abundance, and continuity. Over time, limbs transformed into flippers, tails widened for propulsion, and bodies streamlined for movement through dense fluid. Still, whales retained lungs, warm blood, and the need to surface regularly. Their return was not a reversal, but a continuation shaped by opportunity. The sea remained familiar enough to re enter, even after millions of years apart. Amphibians hold a quieter connection. Their lives unfold between water and land, never committing fully to either. Soft skins allow gas exchange but require moisture. Eggs lack hard shells, leaving them vulnerable to drying. Many species begin life in water, breathing through gills before transitioning to air. This dependence reflects an ancient compromise. Amphibians represent a lineage that ventured outward but remained anchored to conditions close to their origin. Eggs tell a similar story. Early terrestrial reproduction faced a challenge: how to protect developing life from drying while still allowing gas exchange. The amniotic egg solved this by enclosing a private aquatic environment within membranes and shell. Inside, liquid cushions and nourishes the embryo, recreating conditions once provided by surrounding water. Even species that lay eggs far from shore carry a small sea within each generation, sealed just long enough for life to begin. These returns are not failures of adaptation, they reveal continuity. The sea shaped fundamental processes so deeply that abandoning it entirely offered no advantage. Water stabilizes temperature, supports chemical reactions, and buffers development. Wherever possible, life retained access to those benefits, either by remaining near water or by carrying its functions inward. Migration patterns echo this history. Many animals move between marine and freshwater environments, following cycles older than continents. Salmon hatch in rivers, mature at sea, and return upstream to reproduce. Sea turtles cross oceans only to lay eggs on land, guided by instincts tuned to shorelines. These movements trace pathways etched by ancient transitions, repeating them across generations. Even in fully terrestrial animals, traces persist. Embryonic development occurs in fluid. Cells divide, bathed in liquid that mirrors ancient chemistry. Lungs remain moist. Blood retains salts in concentrations reminiscent of seawater. The body itself becomes a vessel, transporting the ocean safely through dry environments. The persistence of these traits reveals something essential. Evolution did not erase history, it built upon it. Adaptations layered over older systems without dismantling them entirely. The sea remained a reliable reference point, one that land never fully replaced. This long shadow reflects continuity rather than nostalgia. Life does not return to water out of weakness, but out of familiarity and efficiency. The ocean still offers conditions that match ancient requirements, reducing the cost of innovation. Where possible, life follows paths already shaped, refining rather than reinventing. Through whales diving into dark depths, amphibians resting near ponds, and eggs cradling fluid life on land, the sea continues to participate in evolution. It remains present not only as an environment, but as an internal condition remembered through structure and habit. The story of leaving the ocean is therefore incomplete without return. Life stepped onto land, expanded its reach, and diversified its forms. Yet it never severed the connection. The sea endures within bodies and behaviors, casting a shadow long enough to touch the present. Life did not arrive on land as a conqueror. It did not survey the surface and claim it through strength or ambition. The transition unfolded for a quieter reason. The world it knew became unreliable, and staying grew more dangerous than leaving. What followed was not triumph, but escape shaped into continuity. For most of its history, life relied on water for stability, chemistry, and protection. When that stability fractured, survival required movement, however hesitant and incomplete. The earliest steps onto land were not declarations of success, they were responses to shrinking margins. Dry ground offered no safety at first, only a different kind of risk. Yet that risk came with possibility, and possibility proved enough. What endured was never certainty, only persistence. Each generation inherited bodies shaped by compromise. They carried the ocean inward, preserving moisture, salts, and chemistry within walls of skin and shell. They learned to tolerate air without trusting it fully. Over time, those tolerances became ecosystems, and those ecosystems became worlds. Seen this way, the story of land life is not one of dominance, but of adaptation under pressure. The land did not invite life, it allowed it gradually, unevenly, and at great cost. Countless forms failed. Many succeeded only briefly. What remains today represents not inevitability, but endurance refined across deep time. This perspective reframes how the living world is understood. Complexity did not arise because conditions were ideal. It arose because they were unstable. Danger narrowed options, and within that narrowing, pathways formed. The forests, animals, and societies that followed are distant consequences of that escape, layered far beyond recognition. The ocean's long influence reminds us that origins are never discarded. Even the most terrestrial lives retain the imprint of their first home. Breath depends on moisture, blood reflects ancient chemistry, development unfolds in liquid cradles. The past remains active, not as memory, but as structure. Earth's history shows how narrow the margins of continuity can be. Small shifts decide whether complexity expands or contracts. Balance holds briefly, then changes. Life persists not by overcoming these patterns, but by aligning with them long enough to continue. In that light, the present moment feels connected rather than separate. The same principles still operate. Environments remain sensitive. Systems respond to accumulation rather than single events. Survival continues to depend on balance held across time, not on permanence. This story invites quiet reflection. not on conquest, but on resilience, not on destiny, but on patience. Life reached land because it had no better option and stayed because it found ways to remain. Every step taken since rests on that ancient necessity. If this journey through deep time has felt calm, strange, or unexpectedly intimate, that response belongs to the story itself. It is not one of spectacle, but of continuity stretching beyond immediate perception. The escape from the sea was not the end of uncertainty, it was the beginning of a longer negotiation with the world. As this exploration settles, the invitation is simple: let the scale linger, let the slowness remain. Consider how much of the present rests on fragile balances held long ago, and how quietly those balances shaped everything that followed. Thank you for drifting through this long story of survival and transition. If you found yourself carried by it, sharing it with others keeps this calm corner of science alive. Until the next quiet journey, this world continues to turn, guided by the same gentle forces that once carried life out of the sea.